Okay, so now we have to learn about echelon form of a matrix. Earlier we have seen how to calculate rank of any matrix. Basically we talked about how to calculate rank of any 3 cross 3 matrix. Now for a matrix whose order is more than 3 into 3, suppose if I have a 4 cross 4 matrix or 3 cross 4 matrix, for these type of matrices, in order to calculate the rank of matrix, first we have to understand this concept of echelon form of a matrix. So the definition of this echelon form of matrix is, a matrix is said to be in echelon form if these two conditions are satisfied. A matrix will be in echelon form if these two conditions are satisfied. Now the first condition is 0 rows. Now this 0 row means if any row is completely 0, then that row is called 0 row. For example, in this matrix you can see that R2 is completely 0, so this R2 is the 0 row. So a matrix will be in echelon form if 0 row must be the last row of matrix. If I have any row in a matrix which is completely 0, then it has to be the last row. So this is the first condition for echelon form of matrix. Now the second condition is each leading entry. So we have to understand the meaning of this leading entry. So leading entry is nothing but first non-zero entry. First non-zero entry is called a leading entry. So each leading entry, for example in R1 you can see that this first non-zero entry is 1, so this is the leading entry. In R2 we don't have any leading entry. In R3 this entry is the first non-zero entry, so this is leading entry. And in fourth row this 2 is the first non-zero entry, and therefore these are the leading entries in different row. So leading entry simply means first non-zero entry. So the definition is each leading entry is to the right side of the leading entry in previous row. So we'll understand the meaning of this thing. See, first if I ask you whether this matrix is in echelon form or not, so the answer is this matrix is obviously not in echelon form. The reason is the R2 is completely 0 and this is not the last row. Okay, a matrix is in echelon form if 0 row is the last row. If there is any 0 row, then it has to be the last row. And second condition, each leading entry is to the right side of the leading entry in previous row. So I am going to interchange some of the row and columns of this matrix, and then we will see whether this matrix is in echelon form or not. So first I am going to make this R2 as the last row. So this will be the last row of matrix A. Now R1 is this row 1, 2, 3, 4. Then R2 is 0, 2, 4, 3. And then the third row is say 0, 0, 2, 5. I have interchanged some of the rows of matrix A, and now this is our new matrix. Now in this matrix you can see that this is our first leading entry, this is second leading entry, and this is our third leading entry. The leading entry means first non-zero entry, so these are the first non-zero entry. In R4 we don't have any leading entry. Now you can see that each leading entry, this leading entry in second row is to the right side of the leading entry in first row, and leading entry in third row is to the right side of the leading entry in second row. So each leading entry is to the right side of the leading entry in previous row, and therefore now this matrix is in echelon form. 0 row is the last row and each leading entry is to the right side of the leading entry in previous row. So this first matrix A is not in echelon form, whereas if I interchange some of the rows, then this matrix is in echelon form. Now next we have to learn second definition of rank of matrix. So the definition of rank of a matrix is, rank of a matrix is number of non-zero rows in echelon form of a matrix. Rank of a matrix is nothing but number of non-zero rows in echelon form of a matrix. So for example, here if I ask you what is the rank of this matrix, so first you have to convert the matrix in echelon form. Now this matrix A is in echelon form. Now how many non-zero rows are there? So this R1 is non-zero, R2 is non-zero, R3 is non-zero, whereas this R4 is completely 0. So here the rank of this matrix will be simply 3. We have 3 non-zero rows, and therefore the rank of this matrix will be 3. So after this we'll learn how to convert any matrix in echelon form and how to find rank of those matrices. Okay, so now with the help of these two examples we are going to see how to convert any matrix in echelon form and then how to find the rank of those matrices. So this is our first example. We have a 3 cross 3 matrix. Now we can find the rank of 3 cross 3 matrix using the properties of rank that we have seen earlier. But here we will talk about how to convert this matrix in echelon form. So first step is you have to start with this element in first row and first column. This element is called pivot element. So you have to start from this pivot element, and your aim is by some row operation you have to convert the element below this pivot element into 0. You have to make this 2 into 0 and you have to convert this 3 into 0. So for that we are going to perform these operations. R2 goes to R2 minus 2 times R1. If I subtract 2 times first row from the second row, then I will create 0 here, and R3 goes to R3 minus 3 times R1. If I subtract 3 times R1 from R3, then I will get 0 here. So if I perform these two operations, then my first row will be 1, 2, 4. The second row is now second row minus 2 times first row. So 2 minus 2 into 1, this will be 0. 3 minus 2 into 2, so 3 minus 4 minus 1. 4 minus 8 minus 4. And then R3 goes to R3 minus 3 times R1. So I have to subtract 3 times R1 from R3. So I will get 3 minus 3, 0. Then I will get 1 minus 6 minus 5. And 2 minus, this will be 4 into 3, 12. So 2 minus 12 minus 10. So after one operation, this will be our matrix A. Now next we have to concentrate on this element in second row, second column. We have to move along this diagonal. So we started with element in first row, first column. We have converted these elements to 0. Now we have to move to this element minus 1. This is our next pivot element. And we have to convert this minus 5 to 0. So for that we are going to perform the operation. R3 goes to R3 minus 5 times R1. If I perform this operation, then our matrix A will be, now first two rows are same. First row is 1, 2, 4. Second row is 0, minus 1, minus 4. And the third row R3, this will be R3 minus 5 times R2. This element is in second row, so we have to perform this operation. So R3 will be R3 minus 5 times R2. So I will get 0 minus 0, 0. Minus 5 minus minus 5. So I will get 0 here. Minus 10 minus 5 into minus 5 into minus 4, so this will be plus 20. So minus 10 plus 20, this will be plus 10. So after two operation, this is our matrix A. Now you can see that this is our first pivot element minus 1. So this is the first leading entry, first non-zero entry. Then this is our second leading entry, and this is our third leading entry. Leading entry means first non-zero entry. Now the definition of echelon form was that each leading entry is to the right side of the leading entry in previous row. So this is our first leading entry. Second leading entry is on the right side of the leading entry in first row, and the leading entry in third row is to the right side of the leading entry in second row. So now this matrix A is in echelon form, and here if I ask you what is the rank of this matrix A, so you can see that all these three rows are non-zero rows. R1 is non-zero, R2 is non-zero, and in R3 also we have one non-zero entry. So all these three rows are non-zero rows, and we have seen that rank of matrix is nothing but number of non-zero rows in echelon form of matrix. So here the rank of this particular matrix will be 3. So this was our first example. Now the second one is we have to convert this matrix in echelon form, and we also have to find the rank of this matrix. Now for any 3 cross 3 matrix, this echelon form is converting the matrix in echelon form and then finding the rank of matrix. This is the best approach to find a rank. The reason is that here you cannot calculate determinant. And so first thing is we have to convert this matrix in echelon form, then only we can find the rank of this matrix. So now we have to start with this element. This element is pivot element. Now it is always better to have one as pivot element, because that will reduce our calculation. That is not rule, but a guideline that if there is option, then you can make one as pivot element. So I can interchange these two rows. If I interchange R1 and R2, then I will get one as pivot element, and this will reduce our calculation. So therefore I am going to write this matrix A as, my first row will be 1, 2, 3, 5. Now R2 becomes R1 and R1 becomes R2. So this will be 2, 4, 0, 6. And then the third row is same, 2, 1, 3, 9. So this is our matrix A after interchanging R1 and R2. It is better to have one as pivot element. So now if I have, this is our first pivot element, and we have to create 0 below this element. So I can perform this operation. R2 goes to R2 minus 2 times R1, and R3 goes to R3 minus 3 times R1. So if I perform these two operations, then our matrix A will be, the first row is same, I will have 1, 2, 3, 5, then R2 is R2 minus 2 times R1, so 2 minus 2 I will get 0 here, 4 minus 2 I will get 0 here, 0 minus 6 minus 6, 6 minus 10 minus 4, then R3 is R3 minus 2 times R1, so again I will get 0, 1 minus 4, so minus 3, 3 minus 6, again minus 3, 9 minus 10 minus 1. So now this is our matrix A, and our next pivot element is this 0, but 0 cannot be pivot element. Okay, this is also very important point. If you have 0 as pivot element, then you have to interchange it with the next row. So now we are going to interchange R2 and R3. Maybe I can do the calculation here. So after this, I am going to interchange R2 and R3. So if I interchange R2 and R3 in this matrix, if I simply interchange R2 and R3, then our matrix A will be, first row is same, 1, 2, 3, 5, then second row will be, third row will become second row, so 0, minus 3, minus 3, minus 1, and then I will get 0, 0, minus 6, minus 4. Now you can see that this is our first pivot element, you have 0 below the pivot element, this is second pivot element, and we had to create 0 below this element, but we already have 0 here. So now this is the echelon form of matrix. These are the three leading entry, minus plus 1, minus 3 and plus 6, and all these leading entry are to the right side of the leading entry in previous row. So this matrix is again in echelon form, and here if I ask you what is the rank of this matrix, so again you have three non-zero rows, R1, R2, R3, all these three are non-zero rows, and we have seen that rank of a matrix is nothing but number of non-zero rows in echelon form of matrix. So the rank of this matrix will be 3. So this was all about echelon form of matrix. First you have to see the pivot element. It is always better to have 1 as pivot element, 0 cannot be pivot element. So here first we have made 1 as pivot element, we have created 0 below it. Now this was our next pivot element cannot be 0, so we have interchanged R2 and R3. Now the moment we interchange R2 and R3, this matrix is in now echelon form, and the rank of this matrix is 3. So this was all about rank of matrix. Now after this we'll talk about consistency of system of linear equations. Okay, so our next topic is consistency of system of linear equation. So with the help of a few basic examples, first we will see what is the meaning of this consistency, what is meaning of unique solution, no solution, or infinite number of solution, and then we'll see what should be the general formula to find consistency. So the first example that I'm going to take is, suppose if I have this system of equations, say x plus y equals to 2, and another equation 2x plus y equals to 3. Now here if I ask you how many solutions are there for this system of linear equations, so basically we have to find those values of x which will satisfy both of these equations simultaneously. So you can easily see that if I solve these two equations, then we will find that the value of x is 1 and the value of y is 1. Right? You can easily solve this equation. You can subtract second equation from first one, so you will get x equals to 1. If you substitute x equals to 1 here, you will get y equals to 1. So this is the solution of this system of linear equation. Now this system of linear equation has a unique solution because only one value of x and y is possible which will satisfy both of these equations simultaneously. You cannot think of any other number x and y which will satisfy both of these equations. So therefore this system of linear equation has unique solution. Unique solution simply means that there is only one solution for the system of linear equation. There is only one set of possible values of the variables x and y which are going to satisfy both of these equations. So this was the first example. The second example that you can think of is x plus y equals to 2 and say 2x plus 2y, this equals to 4. Now here again we have two equations, two variables, but here if I ask you how many value of x and y is possible which will satisfy both the equation. So if you see carefully, the second equation is nothing but first equation multiplied by 2. If I divide the second equation by 2, then I will get the first equation. So basically we have only one equation, and second equation is simply some multiple of first equation. So here we have two variables x and y, and we have to satisfy only one equation. So here if I ask you how many values of x and y is possible, so one value you can think of is 1, 1. If I place x equals to 1, y equals to 1, then it will satisfy this equation. Another value that you can think of is x minus 2, y plus 4. So this value is also going to, this pair of value, this is x, this one is y. So x plus y equals to 2. If I place x equals to minus 2, y equals to plus 4, then this value will also satisfy both of these equations. And similarly, you can think of many other solutions. You can place x equals to 0, y equals to plus 2. So in this way, there are infinitely many other value of x and y which will satisfy both of these equations simultaneously. And therefore, this system of linear equation has infinitely many solution. Infinitely many solution means infinite number of value of variable is possible which are going to satisfy all the equations simultaneously. So first system of linear equation has unique solution. Second system of linear equation has infinitely many solution. Now the third example that we are going to take is, suppose if I have the equation say x plus y equals to 2, and the second equation is 2x plus 2y equals to 6. Now here if I ask you how many value of x and y is possible which will satisfy both the equation. So if you see carefully, the second equation is nothing but x plus y equals to 3. If I divide the second equation by 2, I will get this equation. So now these are the two equations that you have. First equation, x plus y equals to 2. Second equation, x plus y equals to 3. Now here if I ask you how many solutions are there, so first equation is saying that find two numbers whose sum is 2. The second equation is saying find two numbers whose sum is 3. So no value of x and y is possible which will satisfy both the equations simultaneously, and therefore this system of linear equation has no solution. No solution simply means no value of xy is possible which is going to satisfy both the equations simultaneously. So first system of linear equation has unique solution, only one value of x and y is possible. Second system of linear equation has infinitely many solution because many value of x and y is possible which is going to satisfy all the equations. And this third system of linear equation has no solution. Now the first two cases where the system of linear equation has unique solution or infinitely many solution, these two cases are called consistent. Consistent means the system of linear equation will have solution. Either it will have unique solution or infinitely many solution. This first system of linear equation is consistent with unique solution. The second system of linear equation is consistent with infinitely many solution. And if the system of linear equation has no solution, then this system of linear equation is called inconsistent. So I hope the meaning of this consistency is clear. If the system of linear equation has solution, either unique or infinitely many, then it is called consistent. If it has no solution, then it is called inconsistent. Now we are going to see the general formula to find consistency of system of linear equations. So I will explain the concept with the help of three equations, three variables. But the formula or the concept that we will learn, that will be applicable for any number of equation and any number of variables. So suppose if I have this system of equations, say first equation is a1x plus b1y plus c1z, this equals to d1, a2x plus b2y plus c2z, this equals to d2, and finally a3x plus b3y plus c3z, this equals to d3. And we are interested in finding the consistency of this system of linear equation, and we also want to find what is the condition for unique solution and infinite solution and no solution. So first we are going to define four matrices. The first matrix is called coefficient matrix. So the first matrix is coefficient matrix. This coefficient matrix is represented by this capital letter A, and here we are going to write only the coefficients. So our first row will be coefficient of x, y, z. So first row will be a1, b1, c1. The second row will be a2, b2, c2. And the third row will be a3, b3, c3. So this matrix is called coefficient matrix. After this we are going to define variable matrix. Now this variable matrix is nothing but a column vector. This is represented by capital X. And here we will write the variables only. There are three variables x, y, z. So this variable matrix will be x, y, z. Then our third matrix will be constant matrix. So constant matrix is also column vector. This is represented by capital B, and here we will write the constant of the equation. So these are the constants d1, d2, d3. So our constant matrix will be this column vector d1, d2, d3. Now once you have defined these three matrices, then you can write this system of linear equation in matrix form as A into x equals to B. You can write all these three equations in matrix form in this manner: A into x, this equals to B. And this you can easily verify from here. Suppose if I want to calculate A into x, suppose if I have this equation A into x, this equals to B. So what is the meaning of this thing? This is your matrix A. Matrix X is this matrix XYZ, and equals to B. B is the matrix D1, D2, D3. So this equation is A into x equals to B. Now you can see that you can get all these three equations from this matrix equation itself. For example, if I have to equate this element in first row and first column, so I will get A1x plus B1y plus C1z. This will be D1. So this is your first equation. Then A2x plus B2y plus C2z. This will be D2. So this will be the second equation. And similarly, you will get the third equation also. So instead of writing the equation in this form, we can write this system of linear equation in matrix form in this manner: A into x, this equals to B. A is coefficient matrix, x is the variable matrix, B is the constant matrix. Now after this, our fourth matrix will be augmented matrix. Now this augmented matrix is represented by A by B, and this is nothing but coefficient matrix plus the constant matrix. We write augmented matrix, we represent augmented matrix in this manner: A slash B, and this will mean that first we have to write this coefficient matrix. So coefficient matrix is A1 B1 C1, A2 B2 C2, A3 B3 C3. So this matrix is coefficient matrix, and we have to write the constant matrix B. So constant matrix B was D1 D2 D3. Sometimes this line is erased, or so, but you have to understand that the reason before this line, this is representing your constant matrix A, and this is your coefficient matrix A, and this is constant matrix B, and these two combined is the augmented matrix A by B. So now once we have defined these four matrices, then we can find the condition for consistency of system of linear equation. Okay, so now we can talk about consistency of system of linear equations. So these were the three equations in three variables. Now in matrix form, we can write the system of linear equations in this manner: A into x equals to B. We had defined four matrices: coefficient matrix A, constant matrix B, variable matrix X, and the augmented matrix A by B. Now if we want to find whether the system of linear equation is consistent or not, and if it is consistent, then whether it is consistent with unique solution or infinite number of solution. So first step is you have to find the rank of matrix A and the rank of augmented matrix A by B. Calculate the rank of coefficient matrix and also find the rank of augmented matrix. Now there are two possibilities. The first possibility is that the rank of coefficient matrix is equal to rank of augmented matrix. And the second possibility is that rank of coefficient matrix is not equal to rank of augmented matrix. So if the rank of coefficient matrix is not equal to rank of augmented matrix, then in that case the system of linear equation will be inconsistent. Inconsistent means the system of linear equation will have no solution. No value of x, y, z is possible, or no value of variable is possible which will satisfy all the equations simultaneously. So if rank of A is not equal to rank of augmented matrix A by B, then system of linear equation is inconsistent. Now the second possibility was that if the rank of coefficient matrix is equal to rank of augmented matrix, now here in this case the system of linear equation will be consistent. If rank of coefficient matrix is equal to rank of augmented matrix, then in that case the system of linear equation will be consistent. Now in consistent also we had seen two possibilities: consistent with unique solution and consistent with infinite number of solution. So now the two possibilities are, if the rank of coefficient matrix A is equal to rank of augmented matrix A by B and is equal to number of variables n. So for example, if I have three equations and three variables, so here the number of variable is 3, X, Y and Z, these are the three variables. So if rank of A is equal to rank of A by B, and this is equal to number of variables, for this particular example 3, then this means the system of linear equation is consistent with unique solution. So only one value of the variable is possible which will satisfy all the three equations simultaneously. And if rank of A is equal to rank of augmented matrix A by B but is less than number of variables, so if this condition is satisfied, then in this case also the system of linear equation will be consistent, but here you will have infinitely many solutions. Infinite number of values of variable is possible which will satisfy all the equations simultaneously. So this is a very important these are very important results that you have to remember. If rank of A is equal to rank of A by B, then system of linear equation is consistent. Now if it is equal to number of variables, then it is consistent with unique solution. If it is less than number of variables, then it is consistent with infinitely many solution. And if rank of A is not equal to rank of A by B, then in that case the system of linear equation is inconsistent or it will have no solution. So after this, we will take some examples, and with the help of those examples, we will see how to check consistency of system of linear equations. So this is our first problem. The question is, we have to check the consistency of this system of linear equations. Three equations are given. The first equation is x plus y plus z equals to 3. The second equation is x plus 2y plus 3z equals to 6. And the third equation is x plus 2y plus 4z equals to 7. Now we have to find whether the system of linear equation is consistent or not, meaning that we have to find whether any value of variable is possible which will satisfy all the three equations. So first step is we have to start with the augmented matrix. The reason is this augmented matrix A by B, this also includes the coefficient matrix and the constant matrix. So we will start with this augmented matrix A by B. So our first row will be 1, 1, 1, 3. Then our second row will be 1, 2, 3, 6. And the third row will be 1, 2, 4, 7. Remember that these three rows and columns, these are the part of coefficient matrix A, and this is the constant matrix B. And these two combined is the augmented matrix A by B. So this is our augmented matrix. Now our aim is we have to convert this augmented matrix in echelon form, and then we will see what is the rank of coefficient matrix, what is the rank of augmented matrix, and then we'll apply those concepts that we have learned. So in order to convert this matrix in echelon form, we have to start with this first element in first row and first column. This was our pivot element, and we have to create 0 below this element. So if I perform this operation, R2 goes to R2 minus R1, and R3 goes to R3 minus R1. So if I perform these two operations, then I can create 0 below this element 1. So our augmented matrix A by B, this will be, our first row is 1, 1, 1, 3. Then our second row is second row minus first row. So this will be 1 minus 1, 0, 2 minus 1, 1, 3 minus 1, 2, and 6 minus 3, 3. And similarly, the third row is third row minus first row. So R3 is R3 minus R1. So I will get 1 minus 1, 0, 2 minus 1, 1, 4 minus 1, 3, 7 minus 3, 4. So this is our augmented matrix A by B. Now the next step is, this is our next pivot element, and we have to create 0 below this element. So now we are going to perform the operation. R3 goes to R3 minus R2. So now our augmented matrix A by B, this will be, first two rows are same, 1, 1, 1, 3. The second row is 0, 1, 2, 3. And now in place of R3, we have to write R3 minus R2. So if I subtract second row from the third row, I will get 0 minus 0, 0, 1 minus 1, 0, 3 minus 2, 1, 4 minus 3, 1. So now this matrix is in echelon form. Each leading entry, these are the leading entry. So each leading entry is to the right side of the leading entry in previous row. So this matrix is in echelon form. The first three columns are coefficient matrix A, and all these four columns are augmented matrix A by B. Now here if I ask you what is the rank of coefficient matrix A, so you can easily see that for this 3 cross 3 matrix, these three these three columns, first column, second column and third column, you can see that all the three rows are non-zero rows. R1 is non-zero, R2 is non-zero, and in R3 also we have non-zero entry. So the rank of coefficient matrix A, this will be 3, and the rank of augmented matrix A by B, this is also 3. For matrix A by B also you can see that now you have to consider this fourth column also. So all these three rows are non-zero rows. You have one here, one here. So since rank of coefficient matrix A is 3, rank of augmented matrix A by B is also 3. So since rank of A is equal to rank of A by B, and 3 is nothing but number of variables. Here we had 3 variables x, y, z. So this is equal to number of variables. So this means the system of linear equation is consistent. This implies the system of linear equation is consistent and it has unique solution. Unique solution means only one value of x, y, z is possible which will satisfy all the three equations simultaneously. Now if the question was we also had to find the value of variables, so how to solve that problem? So see, at any stage you can get back your equations from this matrix itself. For example, if this was our matrix, so what was the corresponding equation? 1 into x plus 1 into y plus 1 into z, this equals to 3. The second equation will be 1 into x, 2 into y, 3 into z, this equals to 6, and so on. Similarly, here suppose if you want to write the equations from this matrix, so your equations will be 1 into x, 1 into y, 1 into z equals to 3, 0 into x, 1 into y, 2 into z, this equals to 3, and so on. So from this echelon form, if I want to write the corresponding equations, so our equations will be 1 into x, 1 into y, 1 into z, this equals to 3. So x plus y plus z, this equals to 3. Our second equation will be 0 into x, 1 into y, 2 into z, this equals to 3. So y plus 2z, this equals to 3. And finally 0 into x, 0 into y, 1 into z, this equals to 1. Now, so the value of z is directly known to us. Now by doing back substitution, we can find the value of x and y. If I substitute the value of z in our second equation, I will get y plus 2, this equals to 3. This means the value of y, this will be 2. And if I substitute the value of y and z in the first equation, then I will get the value of x. X plus 1, this will be 3. The value of y is 1. So this means the value of x will be 1. So these are the possible value of x. X is 1, y is 1, z is 1. So this is the solution of given system of linear equation. And since only one value of variable is possible, which are going to satisfy all the three equations simultaneously. So therefore the system of linear equation has unique solution. So this was a very basic question. After this, we will take one example which was asked in GATE. So our next question is, this question was asked in GATE 2011. The problem is, three equations are given. These are the three equations: x plus y plus z equals to 6, x plus 4y plus 6z equals to 20, and x plus 4y plus lambda z equals to nu. Now the question it is given that this system of linear equation has no solution. So we have to find which one of these option is correct. So first we have to start from the augmented matrix. So our augmented matrix A by B, this will be, our first row will be 1, 1, 1, 6. Then our second row will be 1, 4, 6, 20, and the third row will be 1, 4, lambda nu. So this is our augmented matrix A by B. Now our aim is, first we have to convert this augmented matrix in echelon form, and then we'll see what should be the condition for this system of linear equation to have no solution. So this is our first pivot element, and we have to create 0 below this element. So we are going to perform the operation R2 goes to R2 minus R1, and R3 goes to R3 minus R1. If I perform these two operations, then we can create 0 below this pivot element 1. So our augmented matrix A by B, this will be, the first row is 1, 1, 1, 6. Then the second row will be second row minus first row. So I will get 0, 3, 5, 14. So this will be our second row. And the third row is third row minus first row. So again I will get 0, 3, lambda minus 1, nu minus 6. So this is our augmented matrix A by B. Now our next pivot element is this 3, and we have to create 0 below this element. So now we are going to perform the operation R3 goes to R3 minus R2. So the augmented matrix A by B, this will be, The first two rows are same, 1 1 1 6. The second row is 0 3 5 14, and the third row will be 0. Now the third row is third row minus second row, so I will get 0, 3 minus 3 is 0, lambda minus 1 minus 5, so this will be lambda minus 6, nu minus 6 minus 14, so nu minus 20. So this is our augmented matrix A by B. Now we have to find what should be the condition for this system of linear equation to have no solution. So for no solution, we have seen that for no solution, the condition is rank of coefficient matrix A is not equal to rank of augmented matrix A by B. This will be the condition for no solution. Now your matrix A is the first three columns, C1, C2, C3. These are the part of coefficient matrix A, and coefficient matrix plus this constant matrix is augmented matrix. So this will be possible if the rank of matrix A is 2 and rank of augmented matrix A by B is 3. Okay, because R2 is non-zero for both coefficient matrix and augmented matrix, so we can play only with R3. So in R3, if I make this lambda minus 6 0, then the rank of coefficient matrix A, this will be 2. If I have 0 here, then for coefficient matrix, this R3 will be completely 0 and rank will be 2. So for no solution, the condition should be rank of A is not equal to rank of A by B. This means the possibility that we can see from there is rank of A should be 2 and rank of A by B, this should be 3. So this implies lambda minus 6 is 0 and nu minus 20 is non-zero. Only then this system of linear equation will have no solution. So this means lambda is equal to 6 and nu is not equal to 20. So this will be the condition for no solution. So you can see that the correct option is option B. Lambda equals to 6 and nu is not equal to 20. Now see, what is the meaning of this thing? Suppose if I have 0 here, and I have some non-zero number here, say I have 2 here. So the meaning of this is that your third equation will be 0 into x plus 0 into y plus 0 into z, this equals to 2. Now we have, so this is the meaning of this third equation. Now you cannot find any value of x, y, z which will satisfy this equation. Whatever be the value of x, y, z, this quantity has to be 0. So if the right hand side is non-zero and you have 0 here, then this system of linear equation will have no solution. So this was very good question. Now with the help of same example, we will see that what should be the condition for unique solution and for infinitely many solution. So the question is over. The problem was we had to find the condition for no solution. The correct answer is option B. But with the help of same example, we can also talk about the condition for infinitely many solution and unique solution. So for infinitely many solution, the condition was that rank of A is equal to rank of augmented matrix A by B and is less than number of variables. Now here you have 3 variables, so this system of linear equation will have infinitely many solution if rank of A and rank of A by B is equal to 2. So if rank of A is 2, this means the value of lambda minus 6 has to be 0. This means lambda is equal to 6. And if rank of augmented matrix A by B is also 2, so this means nu minus 20, this also has to be 0, so this means nu will be 20. So this will be the condition for infinitely many solution. Lambda equals to 6, nu equals to 20. In that case, you will get 0 here, and then whatever be the value of x, y, z, it will always satisfy the third equation. So basically you have to satisfy 2 equations and you have 3 variables, so it will have infinitely many solution. So the condition for infinitely many solution, lambda equals to 6 and nu equals to 20. Okay, this statement is important. Lambda equals to 6 and nu equals to 20. Both of these conditions has to be satisfied. Only then the system of linear equation will have infinitely many solution. And the last one is unique solution. Now the condition for unique solution was that rank of A is equal to rank of A by B is equal to number of variables. Now here you have 3 variables, so this means rank of A has to be equal to rank of A by B, and this has to be equal to 3. So for this, the correct condition will be lambda minus 6, this not equal to 0. There is no condition on nu minus 20. Some students have this confusion that this quantity should also be non-zero, but that is not correct. Only condition is lambda minus 6, this should be non-zero. This means lambda is not equal to 6. See, if you have some non-zero number here, if I have say 2 here, and this quantity is 0, so what is the meaning of this thing? If I ask you what is the rank of matrix A, so rank of matrix A will be 3. All the 3 rows are non-zero. And what is the rank of augmented matrix A by B? So this is your augmented matrix. So augmented matrix is matrix A plus the constant matrix. So the rank of augmented matrix is also 3. This matrix is obviously in echelon form. These are the leading entry. And all the 3 rows are non-zero rows. R1 is non-zero, R2 is non-zero, and in R3 also you have one non-zero entry. So this means whatever be the value of this quantity nu minus 20, if I have some non-zero number here, then in that case you will have unique solution. So the correct condition is lambda minus 6 non-zero, which means lambda is not equal to 6. Now the meaning of this statement, this condition is, suppose if nu minus 20 is 0, suppose if this number is 0 and you have 2 here, so this simply means that 2 into z is 0, which means the value of z will be 0, right? So for unique solution, so this simply means that z will be 0, and if you have some non-zero number here, so that means z is non-zero. So this nu minus 20, this can be anything. Lambda minus 6, this has to be non-zero, and nu minus 20, let me write this thing also, nu minus 20, this belongs to real. This may be any real number. This means nu is any real number. So the condition for unique solution will be lambda not equal to 6 and nu is any real number. We are talking only about real solutions, so therefore nu is any real number. So these are the conditions for unique solution, lambda equals to 6, nu not equal to 20. For infinitely many solution, lambda equals to 6 and nu equals to 20. And for unique solution, the condition will be lambda equals to 6 and nu any real number. So this was a very good problem. After this, we'll talk about homogeneous system of linear equations.